Life happens incredibly fast. And just the time it takes you to blink, literally, countless chemical reactions have fired off inside your cells. But how fast is fast? I mean, how do we even begin to measure the speed of these tiny biological machines we call enzymes? Well, let's dive into exactly that and figure out how we actually clock the speed of life itself. So here's our game plan. We're going to start with the why we even bother measuring enzyme speed. Then we'll hit a really weird puzzle, a mysterious speed limit. After that, we'll uncover the aha moment in the enzyme substrate complex, put some numbers to it with the Michaelis-Menten model, and learn to speak the language of efficiency and affinity. And to wrap it all up, we'll see this stuff in action right inside our own bodies. All right, so first things first, why go through all of this trouble just to measure how fast an enzyme can work? Well, it's really all about understanding the fundamental rules of the road for these reactions. The whole field is called enzyme kinetics, and you can honestly think of it like creating a super detailed performance review for an enzyme. We're not just asking, hey, is it fast? We're asking, okay, how fast? Under what conditions? What makes it go faster? And what slams on the brakes? Getting these answers is the absolute key to figuring out how they actually work. Now, this slide points out a really clever trick scientists use. See, a reaction is always a moving target, right? The amount of fuel, the substrate, is constantly being used up. So to get a clean, reliable measurement, they measure the speed right at the very beginning of the race. This is what we call the initial velocity, or V0. A lot of scientists will say V0. It's that moment when the substrate level is super high and hasn't really changed yet. It's kind of like clocking a sprinter's speed in those first explosive steps out of the starting blocks. And that little trick leads us to this really strange observation, a puzzle that totally stumped early biochemists. You would think, logically, that the more fuel you give an enzyme, the faster and faster it should go, right? Just keep adding more? Well, it turns out it's not quite that simple. Just look at this graph. Along the bottom, on the x-axis, you've got the concentration of substrate. That's the enzyme's fuel. And at the side, on the y-axis, is the reaction speed. So as you can see, when you start adding more substrate, the reaction speeds up. Great. But then, something weird happens. It starts to level off. It hits this ceiling, this plateau, a maximum velocity that we now call Vmax. You can dump in all the substrate you want at that point. It's just not going to go any faster. So, of course, the big question is, why? Why on earth does the reaction hit this speed limit? It's like you're flooring the gas pedal in your car, but the speedometer just gets stuck. What is going on? The answer to this puzzle was a total game changer. I mean, this was the aha moment that really unlocked our entire modern understanding of how enzymes do what they do. And this right here is the whole solution. The reaction isn't just one step. See, the enzyme, that's E, has to first physically bind to its substrate, S, and form this temporary middleman called the enzyme substrate complex, or ES. Only then can the reaction happen and the enzyme can release the product, P. That middle step, the ES complex, is everything. So this binding step, that's our bottleneck. Think about it. An enzyme only has so many active sites, like a factory with a limited number of assembly lines. When you keep adding more and more substrate, eventually all of those active sites are occupied. The enzyme is completely saturated. It's working flat out, as fast as it possibly can. And adding more substrate at that point, it just creates a waiting line. And that is our Vmax. Okay, so how do you take this amazing observation and turn it into something you can actually use, something predictive? Well, once scientists understood the ES complex, the next logical step was to build a mathematical model to describe it. And this became the famous Michaelis-Menten model, which is built on just a few really clever assumptions. First, the model assumes there's way more substrate than there is enzyme, so the substrate level basically stays constant for our measurement. Second, like we already talked about, we only look at that initial velocity, which means we can pretty much ignore any product trying to turn back into substrate. And third, and this is the big one, it assumes that the amount of that ES complex reaches a steady state, meaning it's being formed just as fast as it's breaking down. These three simple rules let us cut through the noise and get a really powerful equation. So, we've got this fancy model. What's the payoff? What does it actually tell us? Well, it gives us a really precise language to talk about and, more importantly, compare how different enzymes perform using two key numbers. First up, you have Km, the Michaelis constant. So technically, it's the concentration of substrate you need to get the enzyme to work at half its top speed. But what it's really telling us is all about affinity, basically how sticky the enzyme is for its substrate.
And here's the key thing to remember. A low Km means high affinity. The enzyme doesn't need a lot of substrate around to get going because it grabs onto it so tightly. Our second number is kcat, which we call the turnover number, and this one is just pure raw speed. It's the maximum number of substrate molecules that a single enzyme molecule can process or turn over every single second when it is completely saturated. This is our enzyme with the gas pedal completely floored. So you might be wondering, which is more important, having a high affinity or having a high speed? And the answer is both. The ultimate performance metric, the one number that tells you almost everything, is its catalytic efficiency. And you calculate it by taking kcat and dividing it by km. This one value tells you how good an enzyme is at both finding its target and, once it has it, getting the job done. Now, I promise, this isn't just a bunch of abstract math. Let's look at some real-life examples. You're about to see just how mind-bogglingly efficient these little machines can be and why our very lives depend on it. I mean, just take a look at this table. The values for kcat and km span these enormous ranges. We're not talking a little difference here and there. We're talking many orders of magnitude. It's because nature has perfectly tuned each enzyme for its very specific job. So let's meet a couple of biological superstars. Okay, here is a literal life or death problem for you. When a nerve wants to tell a muscle to contract, it releases a chemical called acetylcholine. But for you to relax that muscle or for it to contract again, that chemical signal has to be shut off instantly. If it isn't, your muscle gets locked up, basically in a state of paralysis. So what's the solution? It's an enzyme called acetylcholinesterase. And its kcat, its turnover number, is 14,000. Let that sink in. A single molecule of this enzyme can find and destroy 14,000 molecules of acetylcholine every single second. That unbelievable speed is what allows you to have such fine, rapid-fire control over all of your muscles. Okay, here's another huge biological challenge. To digest food, your stomach has to become incredibly acidic, right? But it's sitting right inside your body, which is, for the most part, neutral. So how do these special cells, these parietal cells you see here, pull that off? They need to generate a massive and super fast supply of protons to create that acid. The hero of this story is an enzyme called carbonic anhydrase, and its kcat is a staggering 1,000,000 reactions per second. It is one of the fastest enzymes known to science, and this absolutely incredible turnover rate is what makes something as basic as digestion even possible. All right, so let's just quickly recap the big ideas. First, enzyme speed isn't infinite. It hits a very real speed limit because it has to form that enzyme substrate complex. Second, the Michaelis-Menten model gives us the language Vmax and Km to describe and quantify all of this. Third, the ultimate report card for an enzyme is its catalytic efficiency, which is just kcat over Km. And finally, and most importantly, this efficiency isn't just some number in a textbook. It is absolutely critical for pretty much every process that keeps us alive. And all of this leaves us with one last, really fascinating question. If nature has spent billions of years perfecting these incredible molecular machines, what happens when we, as humans, intentionally try to stop them? When we design molecules specifically to get in their way and slow them down? Well, that's the fundamental principle behind countless life-saving drugs. And that's the story for another explainer.